So welcome everybody to the last session, last group of talks in this day-long conference. I hope everybody's been enjoying them. We're going to start it off with Aidan Lorenz from Vanderbilt University, who's going to tell us some things about hyperbolic fibered three manifolds and pseudo-Anosov homeomorphisms.
All right, thanks. Thanks for the invitation, and thanks everyone for coming. Yeah, so let's get right into it. I just want to start by recalling some of the basic definitions and some notation. So for us, S will be a surface, just a topological two-manifold, no assumptions on smoothness or anything like that. And MCG of S, the mapping class group of S, just as a reminder, is the group of orientation-preserving homeomorphisms of our surface, but only considered up to homotopy. And potentially the most important theorem in the theory of mapping class groups is the so-called Nielsen-Thurston classification, which says the following thing. It says every element of the mapping class group of a surface is one of the following three things. It's either finite order. Okay, so I think we all know what that means. It's reducible, which maybe I'll explain that by means of an illustration. So you can imagine we have just a genus 3 surface like this. And imagine the homeomorphism where we rotate it counterclockwise one click. This is reducible because there's a collection of disjoint, simple closed curves that I've drawn in red here, which is preserved by this homeomorphism. So that's what it means to be reducible. And they're called reducible because the idea is that you can take one of these homeomorphisms, cut your surface along the reducing curves, and your homeomorphism is still a homeomorphism of the resulting surface, so you can reapply the classification there. And by the way, finite order and reducible are not disjoint, right? Like this homeomorphism I drew here is both finite order and reducible, but they're different in that there are finite orders which are not reducible, and there are reducibles which are not finite order. And the third option is pseudo-Anosov. And one definition you can take for pseudo-Anosov is that it's anything which isn't finite order or reducible. So that's kind of one nice way of understanding things. But if you take that as your definition, then this theorem isn't much of a theorem. So luckily, there's kind of a more tangible definition of what it means to be pseudo-Anosov. And I won't actually kind of write down the formal definition because it's a little bit long-winded and maybe a little complicated. But the idea is that a pseudo-Anosov takes your surface, stretches it in one direction, and compresses it in a transverse direction. And the factor by which it stretches and compresses are reciprocals of one another. So you can see in this little drawing I have here that you have a vertical foliation of your surface in red, at least I drew a little local picture of it, and a horizontal foliation of your surface in blue. And the pseudo-Anosov phi is stretching along the blue foliation and compressing along the red foliation by reciprocal factors. And the factor by which your pseudo-Anosov stretches or compresses is just called the stretch factor, or sometimes called the dilatation. By the way, one thing I should mention is that these foliations necessarily have singularities. So there are points that look kind of like this in your foliations. It's impossible to foliate a hyperbolic two-manifold without singularities like this. So that's not necessarily super important for us right now, but it'll come up a little bit later. Well, so I guess the moral of this, one of the morals of this theorem is that the pseudo-Anosov homeomorphisms or the pseudo-Anosov mapping classes are kind of the most interesting ones. I mean, finite order and reducible are kind of simple or understandable in certain ways. And the pseudo-Anosov ones are like the interesting ones, algebraically, topologically, dynamically, basically every way. So naturally, there's a lot of content studying these things, and by extension, their dilatations or their stretch factors. So one example of a result on their stretch factors is that if you look at just the closed surface of genus G, call it SG, so it has no punctures, no boundary components, just a genus G surface. And you can consider all the pseudo-Anosov homeomorphisms of that surface, and that gives you like a spectrum of stretch factors. And this proposition, this fact, is that the smallest dilatation actually exists. Like the infimum is realized. There's a well-defined smallest dilatation homeomorphism on a closed surface of genus G. And this leads to some kind of natural questions, like for fixed G, what is delta G? Like, can we compute these numbers? And another question, like if you're thinking about delta G as a function of G, well, what is the function? Like, how is delta G related to G? And the answers to these things, well, they vary. For the first question, really not much at all is known. I think the only thing that's known is genus 2. Cho and Ham showed that delta 2 is like 1.72 something. But that's the only genus for which this is known. So evidently that's a hard question. It's hard to just pick a genus and figure out what delta G is. For the second question, there's a famous theorem of Penner which says that log of delta G grows like 1 over G. So let's maybe take a second to say something about this. So what this means is that there exists some constant C so that the following inequalities are satisfied. Now, if you just exponentiate every side of this, you get the following, right? In particular, this says that as you take the limit as G goes to infinity of delta G's, you approach 1. But now even more, if you put G in the exponent everywhere, you wind up with this set of inequalities. So you have uniform bounds on delta G to the G. And this has led to the now famous open question asking about this sequence, whether this sequence delta G to the G going across all G's, whether this sequence converges or diverges. That's a famous open question, and it's not exactly the question we'll be approaching in this talk, but we'll be approaching closely related questions. So this hopefully serves as the motivation. And the means by which we'll be like studying such questions is through fibered 3 manifolds. So let's take a quick second and remember what these are. So there are a couple ways you can define fibered 3 manifolds, but I kind of like this constructive definition. So a 3 manifold is fibered if it can be constructed as a mapping torus. And a mapping torus is just the following simple thing. You start with a surface and a homeomorphism of your surface. You take your surface, cross it with the interval, and then glue the top to the bottom by your homeomorphism. So that's what this diagram and this formula kind of indicate. It's called fibered because, when you do that construction, you wind up with a 3 manifold, and it's called fibered because there's a map from that 3 manifold to the circle S1, where the fibers, the preimages of points, are all homeomorphic to the surface you started with. The gluing map is called the monodromy, and there's a famous theorem of Thurston's, which was, I guess, part of his whole geometrization program, which says that the 3 manifold that you wind up with is hyperbolic if and only if the monodromy is pseudo-Anosov. So that's kind of the link between these fibered 3 manifolds, hyperbolic fibered 3 manifolds, and pseudo-Anosov homeomorphisms. In fact, the link between the two things is even a little bit nicer. So Thurston also defined what's now known as the Thurston norm, which is actually a pseudo norm on the second real homology of such a 3 manifold. And I'll describe to you how to define this thing on integer classes. So if you fix a second homology class with integer coefficients, you can represent such a class as an embedded surface in your 3 manifold. So if you fix a class and look at all the embedded surface represented, all the embedded surfaces that represent this class, each of them has, an Euler characteristic, and we say that the simplest embedded surface representative for a class is the one where the Euler characteristic of the surface is the smallest. The absolute value of the Euler characteristic is the smallest. And so you define the Thurston norm to be the absolute value of the Euler characteristic of the simplest surface representative. Okay, so and then you define, and then you extend it to the rationals with just by linearity, and extend to the reals, I guess, by like continuity. So that defines a pseudo norm on H2MR, and it has some really nice properties. So first of all, the norm ball, the unit ball of that pseudo norm, which people refer to as the Thurston norm ball, it's polyhedral. So it has, like, we can refer to top dimensional faces of the unit ball. And it has the property that each cone over any top dimensional face of the unit ball, either all the integer points in that cone represent fibrations or none of them do. So let me explain that using this picture here. So in this picture, well, here H2MR, we're imagining, has dimension 2, say, and this red square is our Thurston norm ball. Here's one of the top dimensional faces that's highlighted in red, and the orange lines are showing the boundary of the cone over that face. And the green points are all the integer points inside that cone. What it means for an integer class to represent a fibration is that, every integer class has a simplest surface, simplest embedded surface representative, like we talked about, and it represents a fibration if you can build this 3-manifold as a mapping torus from that simplest embedded surface representative. So the point is that inside this fibered cone we see here, either every single one of these embedded surface representatives for these points represents a fibration, or none of them do. So this means that, like, in this picture, if this is a fibered cone in that every one of these represents a fibration, we're really getting our hands, we're using one manifold to get our hands on infinitely many pseudo-Anosov monodromies. Right. So I should say it's like a little bit hard to think about visually how you could get a 3-manifold as a mapping torus in even 2 different ways. Like, imagine you take a genus 2 surface, some homeomorphism of it, build a mapping torus. Apparently, in a lot of cases, you can get that same mapping torus from a completely different surface, starting with a completely different surface, which is hard to think about visually. But anyway, it's possible. Right, so yeah, so as I just said, if the Betti number is larger than or equal to 2, M fibers in infinitely many ways. So we get our hands on infinitely many pseudo-Anosov monodromies. By the way, why does the Betti number need to be greater than or equal to 2? Well, if it's 1, then the fibered cones are just lines, and really we only care about primitive points in homology here, because if you have a non-primitive point, then the simplest surface representative is a disjoint union of surfaces, and we really only care about pseudo-Anosovs on connected surfaces. So anyway, primitive points are the ones we care about. Right. So this leads us to an idea. We can instead study delta G MF, this quantity I'm calling delta G MF, which we define in the following way. It's, you fix a 3-manifold and you fix a fibered face, a hyperbolic fibered 3-manifold, and you fix a fibered cone of that hyperbolic fibered 3-manifold. Well, if you're looking inside a fibered cone, as we saw on the last slide, every integer class represents a fibration. Maybe some of them, maybe some of the monodromies are on surfaces of genus G. Among those that are, coming from surfaces of genus G, you pick out the smallest dilatation one. That's what this quantity delta G MF is. There's a small little aside in parentheses there about Dane fillings, which is a bit of a technical point, and maybe I'll mention that at the end if there's some more time. Okay. But so right, we're not exactly studying the original quantity delta G, we're studying the smallest dilatation homeomorphism that, quote, comes from a given 3-manifold and fibered face thereof. Okay, so it's a nice enough idea, but the question is, like, is that actually any more tractable than just studying delta G itself? And the answer is yes, in large part because of this theorem of Fried. And before I state the theorem, I want to just discuss a little bit this function here, lambda bar, which is called the normalized dilation. It's defined, okay, so technically it's not defined on all of H2MR, it's only defined inside fibered cones in H2MR, but you define it on integer classes by, inside a fibered cone, by saying, well, an integer class has a monodromy associated to it, because inside a fibered cone, an integer class represents a fibration, so it has a monodromy associated to it. We're assuming our manifold M is hyperbolic, so by our theorem of Thurston, the monodromy is pseudo-Anosov, so right, it has a dilatation. So you take that dilatation and raise it to the power of the Thurston norm. That's called the normalized dilation, and you can extend it to all points inside a fibered cone, not just the integer ones. And the theorem is that this function is strictly convex, constant on raised through the origin, and goes to infinity at the boundary of the cone. So those three things you can represent like with this blue line here, right? So this blue line is like going to infinity at the boundary of the cone. It's, well, strictly convex. And, well, this function is constant on raised through the origin. So really, just drawing a line like this encapsulates all the information, right? Like this point has the same normalized dilation as this point, has the same normalized dilation as this point. This purple ray here is going straight through the minimizer of this normalized dilatation function, the minimum, which again exists because of strict convexity. Right, so this is a nice theorem, and one more thing I want to say about it is that the definition of the normalized dilatation on the integer classes looks eerily similar to delta G to the G, right? Delta G to the G is like a dilatation raised to a genus power. Here on integer classes, we have like a dilatation raised to a Thurston norm power. But remember, like the Thurston norm is just an Euler characteristic. So this is like a dilatation to an Euler characteristic power. So very close to dilatation to genus power. So what can we do with this theorem? Well, in the closed case, so let's fix a closed hyperbolic fibered 3 manifold and one of its fibered cones F, or a fibered face F. By the way, by a closed hyperbolic fibered 3 manifold, I just mean it has no torus boundary components. No, that wasn't a typo. It is freed. Yeah, no L at the end. Yeah, so fixing a closed hyperbolic fibered 3 manifold, it has no boundary components. And maybe we can say a little bit how you might get torus, like how you might get boundary components on one of these things. Imagine you're building a mapping torus and you start with a surface that has, say, a puncture on it. I'm not really going to distinguish between punctures and boundary components. I guess the distinction isn't that relevant for us. But if you start with a surface with a puncture on it and then build the mapping torus, well, that puncture kind of travels around in the circle direction. And in the resulting 3 manifold, you wind up with a torus boundary component or a cusp. But again, not really going to distinguish between punctures and boundary components. So that's how you get a torus boundary component on one of these 3 manifolds. So the context of this theorem is that we don't have those things. We have a closed hyperbolic 3 manifold. And you fix a fibered face F and let M be the minimizer of Fried's function, the minimizer of this normalized dilatation function from the last slide. Then the theorem is that delta G MF to the G converges to the square root of that minimizer as G goes to infinity. A couple notes about this is that M being closed means that the fiber surfaces have no punctures or boundary. And that's nice and kind of an easy, simple situation, because in that case, when we're looking at the Thurston norm of elements, remember this is like absolute value of Euler characteristic, the expression just has, is just 2 times the genus minus 2. As in, there's no extra term having to do with the number of punctures or boundary components. So if your Thurston norm has just this simple expression, 2 classes have the same Thurston norm if and only if they're on the same, two classes have the same Thurston norm if and only if they have the same genus. So level sets of the Thurston norm are in bijection with genuses of vibrations. So like, how do you go about finding the smallest dilatation genus G homeomorphism coming from this manifold and fibered face? Well, all you have to do is go to the level set of the Thurston norm where that genus is represented, and take the class which is closest to this minimizing ray of Freed's. There's a small technicality, okay, and then those things like are projectively converging to that minimizing ray. So well, so you get the result listed here. The one kind of, I guess, tricky part, or the only tricky part of this theorem is that you really have to find primitive classes converging to the minimizer for each of the genuses, not just any class. Again, primitivity, so you get connected, so you get pseudo-Anosovs on connected surfaces. And that takes like, I don't know, a bit of work using some, I don't know, what I thought was like kind of random number theory stuff. Okay, so that's the closed case. What about the non-closed case? Well, things get a lot harder in the non-closed case. And I probably won't say too much about how, but just to give a little bit of an idea, when your three manifold's not closed, it has torus boundary components. That means your fiber surfaces have punctures or boundary. And therefore, the expression for the Thurston norm, we now have, like in our Euler characteristic expressions, a term that takes into account the number of punctures or boundary components. And that means that like our level sets of our Thurston norm are no longer in bijection with the genus. You know, there's not a one-to-one correspondence between the genuses and the level sets of the Thurston norm. One genus could be represented on a bunch of different level sets of the Thurston norm just by altering the number of punctures you have here. And that makes things kind of quite a bit more complicated. There's some other reasons why things get more complicated in the non-closed case too, but maybe I'll leave it at that for now. But there is some progress in this case. So for example, if the rank of the second homology is 2, then it turns out that the number of punctures of any minimal surface representative of any primitive class is bounded. So there are only finitely many options for the number of punctures one of these classes could have. So that means that if you fix a genus, it actually only lives on finitely many level sets of the Thurston norm. Okay, so that's helpful. And a corollary of that, it's not exactly an obvious corollary. It takes a little bit of work, but the corollary is that the limit of these delta G MF to the G quantities is at least bounded below by the square root of the minimizer of Freed's function. I suspect the reverse inequality is true, and I think I can almost prove it, but not quite. But anyway, this gives us a lower bound. And then in more generally, I mean, in the non-closed case where the rank of the homology is larger than 2, I don't know, it seems pretty hard to, I haven't made much progress in that arena. It seems pretty hard to do these same types of arguments. So just to finish off, I want to bring things back to the original question about this sequence of delta G to the G's. So how do these like delta G MF quantities relate to just the regular old delta G quantities? And the answer to that lies in a theorem from Farb, Leininger, and Margalit from 2011, which says that the set of mapping tori of fully punctured small dilatation pseudo-Anosovs is finite. So by fully punctured, I mean, remember our pseudo-Anosovs necessarily, the foliations along which we stretch and compress necessarily have singularities. So fully punctured means at all those singularities you puncture and then create the mapping torus. So you wind up with a mapping torus with torus boundary components. And if you do that for all of your smallest dilatation pseudo-Anosovs, you wind up with just a finite collection of mapping tori. So if you can understand like delta G MF for these finite, for this finite collection of manifolds M, then you can maybe say something like what I have listed as a conjecture down here, that this sequence has finitely many accumulation points, which isn't quite converging, but it kind of points in that direction. By the way, maybe I should say, as far as I can tell, it seems like the sentiment is that this sequence converges. In fact, it's possible that the set of mapping tori from Farb, Leininger, Margalit's theorem is that it seems possible that this is actually just a singleton singleton set, that there's just one mapping torus where all the smallest dilatation pseudo-Anosovs are actually represented on Dane fillings of that single 3-manifold. So anyway, I'll leave things there. I have a bunch of references. So thanks everyone for listening.
All right. Thank you, Aidan. Does anybody have any questions? You can unmute yourself. I had something. So is there any known bounds on C there for you? You know that delta G to the G has to lie between two bounds. Do you know what those values are? Are those explicit?
Yeah, I think they are explicit. I don't know what they are though.
Okay, sure. If there's no other questions, let's thank Aidan again.